All right, so now what we're going to do is talk about section 7.1, which is really going to involve us solving more trig equations and using some identities. So far we've used the basic definitions and relationships to work with our trig expressions. But now what I'd like to do is dig a little bit deeper so we can start investigating some other applications. So what if I said, for example, I want you to solve, say, y equals x squared minus x. And I want you to solve that, say, set equal to 0. Okay, in other words, we want to solve x squared minus x equals 0. Well, how would we go about doing this? Okay, please don't forget all your techniques from college algebra. They're all going to be coming right back here. Notice we have a quadratic, it's set equal to 0. So our first step would be to factor. These have a common factor. We can pull out an x. If I pull out an x, I'm left with x minus 1. And now what I can say is I have the product of two things equal to 0. So either the first one is equal to 0 or the second one is equal to 0 or potentially both. So my possible solutions here are x equals 0 and x equals 1. Okay, this is something that we do in our college algebra. But what if I change that? What if I have this function, y equals sine squared x minus sine of x? And I want to solve that equal to 0. The same techniques work. And I understand this looks a lot more complicated, but I claim it's the exact same sort of process, okay? Notice we have this squared, we have just one of them. I can pull out a sine x, and if I factor that out, I'm left with sine x minus 1. I still have my 0 property. I can say, well, either the first term is equal to 0 or the second term is equal to 0. Well, where is my sine of x equal to 0? And let's just do this in the interval from 0 to 2 pi. Well, I know that's the case at 0 and at pi. This second one, this is certainly a trig equation we can solve. I have sine x equal to 1, and I know that's the case at pi over 2. Okay, so what I really want to emphasize is these are going to look more complicated because they're going to be trig functions instead of quadratics or various polynomials, but the same techniques hold. The other thing that I would really urge you to do is on page 454 of your textbook, there's a whole bunch of identities. We've used them. We've got the Pythagorean identity, sine squared plus cosine squared equals 1, the negative angle identities, and also just the reciprocals. There's no need to memorize these, but have them in front of your face and familiarize yourself with them because this is what we're going to be using. Okay, so what I'm going to do now is take those techniques that we did in chapter 6 for solving trig equations, and we're just going to get a little more involved, but it's mostly just an extension of that. So I'm going to take us through some examples so that you can see the thought process and the techniques that you can take forward. So one example is, what if I have, and this kind of goes back to what we were doing in chapter 6. What if I want to solve this guy? Okay. Okay. And again, this is very similar to ones that we were doing in chapter 6, but I think it's a really nice way to have these things tie over. Okay. Well, what was our first step? It was to isolate our trig function. In other words, we can divide both sides by 8. And I claim then I'm solving sine of pi over 2x is equal to 1/4. Okay. Now, again, We have a more complicated expression in here, so I'm going to use my technique of substitution. I'm going to say, let's let u be equal to pi over 2x. In other words, what I'm wanting to solve is sine of u equal to 1/4. All right, so this is, we're wanting, notice this is not some common value that we're aware of. So we're going to be using our calculator here, okay? Again, it's not 0, 1, -1, 1/2 √3 over 2 or √2 over 2. Okay, those are our common values. So I say, well, I'm wanting to find my values of u so that my sine is positive. I know that my sine is positive in my first quadrant and my second quadrant. So once I find my first quadrant angle, that will give me my reference angle for the second quadrant. So how do we get to this u? Well, again, what we do is we take the inverse sine of everything. Okay, on our left side, these are inverse functions, they undo each other. So I'm going to have the inverse sine of 1/4. Now, again, I'm going to be using my technology in order to do this. Be sure that you're in the correct mode. In this sort of situation, we're going to want to be in radian mode. So if I use my calculator to hit inverse sine of 1/4, what I'm going to get is u to be about 0.2527. This is my value in my first quadrant. Now, I also need a second quadrant value because there's two quadrants in which my sine can be positive. Well, notice this is just going to become that reference angle. So what I'm going to do in order to find the second quadrant angle is I'm going to take pi minus 0.2527. And if I do that, I will get, I'm doing it as we talk, my other value to be about 2.8889. Okay, so those are my values of u. I'm not done, okay? Why am I not done? Because notice my original problem was asked in terms of x. I need to answer it in terms of x, but I have both of these values of u. So I'm going to say, well, u is the same as pi over 2x. So I have pi over 2x is equal to 0.2527. And if we want all solutions, then that's just plus 2k pi. And I have pi over 2x is 2.8889. And if I want to consider all coterminals, again, I could put plus 2k pi. Okay, but I don't want pi over 2x. I just want x. So how do I get x alone? I multiply everybody by, 2 over pi, the reciprocal here. So I'm going to take 0.257 times 2 divided by pi, and I'm going to get about 0.1608. Use your calculator, you'll see how that goes. And then notice here, I'm going to get plus 4k. And over here, if I take 2.8889 and multiply that by 2 over pi, I'm going to get x to be about 1.8939, again, plus 4k. Okay, so if we just consider going one more time around, well, I could say that one solution is 0.1608 and then 4.1608. And one solution for this guy is 1.8939. And if I set k equal to 1, then my other solution is going to be 5.8939. So notice what we've done here has really followed from what we did in our previous section. All right, let's solve another one. What if now I want us to solve for t, and I'm going to do it in the interval from 0 to 2 pi. And let's have this one be 24 sine t times the cosine of t equals -6 sine t. Okay, notice these are getting funkier, but they're really fun. Okay, so what do I do here? Well, notice in the first example that we did, we went back to the whole idea of factoring. So what I'm going to do is kind of keep that theme in mind. I'm going to move this term over to one side because I know that if I can factor things set equal to 0, that I have some techniques that I can use moving forward. So I can add this to both sides. So I'll get 24 sine t cosine t plus 6 sine t equal to 0. And I look at those two terms and I say, I can pull out a 6 sine t. And if I do that, I claim I'm left with 4 times the cosine of t plus 1. Notice I have the product of two things equal to 0. So either my first one is equal to 0 or my second one is equal to 0. Okay, so let's get at each of these individually here. So here I can isolate my trig function. I have that the sine of t is equal to 0. And this is on my unit circle. And I know that this happens at t equals 0 and t equals pi. Okay. Here we want to isolate our trig function. So the first thing we would do is subtract 1 from both sides and then divide both sides by 4. Notice I have my cosine equal to a negative number. Okay. So I've got to consider what quadrants does that happen in. Well, where is my cosine negative? My cosine's negative in my in my second quadrant and in my third quadrant. So what I need to do is first find my reference angle. In other words, first find where this would be in our first quadrant, because that will become our reference angle elsewhere. So I take the inverse cosine. We can just do of 1/4. Again, make sure you're in radians. And the inverse cosine of 1/4 gives me about 1.318. All right, that is my first quadrant angle. Notice that becomes my reference angle in my second quadrant. In other words, I can take pi minus 1.318. So in my second quadrant, I'm going to get a value of about 1.823, let's see, 6 if I want to round. And then in my third quadrant, again, this is going to become my reference angle again. So now I'm going to take pi plus that value. So I can take pi plus the 1.318, and my other value is going to be 4.4596. Okay, so same ideas. Notice the only difference here is that we're factoring. All right, let's do a few more just so that we kind of get some good ideas of what we're looking at here and what we might encounter. So suppose my next example, and again, I'm going to solve just in my first one rotation. What if I have 2 sine squared x minus sine x minus 1 equal to 0? Oh boy, that looks like a lot, but let me just change this a little bit. What if I have 2x squared minus x minus 1? Is this something we can solve? I claim we can, and ideally we can in a mode of factoring. In my next example, you're going to see that life is not always as ideal. But notice, if you were given this polynomial here, you could factor this to be 2x plus 1 times x minus 1. Well, notice the only difference is here we just have a plain old x, and here I have a sine x. So using that, I claim what we would have then is for this guy up here, 2 sine x plus 1 times sine x minus 1 equal to 0. And if you don't believe it, multiply this out. You'll see that you get where we started from. Okay. Again, I have the product of two things equal to 0. So either the first one is 0 or the second one is 0. Isolate your trig function. Here I'm solving sine x is -1/2. And I know that my sine is negative in my third and fourth quadrant. I know the sine of x equaling 1/2 is one of our very common angles. That's pi over 6. So I know that pi over 6 is going to be my reference angle in my third quadrant. So pi plus pi over 6 is 7 pi over 6. And you could put that in decimal form by multiplying that out if you'd like. And if pi over 6 is my reference angle in my fourth quadrant, well, I take 2 pi minus the pi over 6, which is 11 pi over 6. In this second scenario, I'm solving sine of x equal 1, and I know that happens at pi over 2. All right, so what if I have something like this? 3 sine squared x minus 4 sine x minus 4 equal to 0. All right, well, we could ask ourselves, can we factor this? And in fact, we actually can. Yeah, we can. So let's do that. Notice if I have 3x squared minus 4x minus 4 equal to 0. Let's see, what are we going to have? We have 2. Yes. So what? 3x squared. So minus 6x plus 2x gives me minus 4x and then minus 4. Notice it's a lot easier to digest looking at it like this. So now what I'm going to do is rewrite this, but use my sine function instead. So I have 3 sine x plus 2, sine x minus 2 equal to 0. So either my first one is equal to 0 or my second one is equal to 0. All right, so in this first one, if I isolate my trig function, I'm solving the sine of x is what? -2/3. Okay. And I know that my sine is negative in my third and my fourth quadrant. So the first thing I need to do is get my reference angle. Okay. So in order to get my reference angle, again, be sure you're in radians. I'm going to take the inverse sine of both sides. So I'm just going to do the inverse sine of 2/3. If I find the inverse sine of 2/3, again, by using my calculator, that's going to give me 0.7297. So in order to find my values in my third and fourth quadrant, well, in my third quadrant, I'm going to say, well, that's pi plus 0.7297. So my third quadrant in radians would be 3.8713. And then if this is my reference angle in my fourth quadrant, what I'm going to do is take 2 times pi and then subtract off 0.7297. And my other solution for this guy is going to be 5.5535. Okay, notice it's the same techniques again and again. All right, well, let's now go over here. I have sine x to isolate my trig function equal to 2. Now, you could say, well, the sign is positive in the first and the second quadrant, but one thing you have to ask yourself is the sign ever equal to 2? No, that's not at all in the range. Remember, the range of your sine and your cosine function is from -1 to 1. So there's no solution for this part. Therefore, these are your only 2 solutions. Now, if you didn't put that together, you could say, well, compute inverse sine of 2. And if you put that in your calculator, which I did, you're going to get an error because we're outside. Okay? So be aware of these things. Our sine and cosine are always between -1 and +1. Okay. So what if I have this? Suppose now I want to solve cosine squared x equals 4 sine x. Okay, well, we could think about saying, well, why don't we get everybody on one side of the equation? But even if I was to move this 4 sine x over here, there's nothing I can do to factor these because this only has a cosine and this only has a sine. So I then ask myself, is there a way that I can write this just in terms of one trig function? And yes, there is. Remember, we have sine squared plus cosine squared is 1. I claim then I can say that the cosine squared, getting that alone, is 1 minus sine squared. So I can rewrite my left-hand side as 1 minus sine squared x equals 4 sine x. Notice now I have one trig function. I can move everybody to one side. I'm going to move them to my right side because I always like a positive in front of my squared term. So I'm solving sine squared x plus 4 sine x minus 1. Now, if you want to say, can I factor that? Well, what we're essentially asking is, can we factor this, right? X squared plus 4x minus 1. I claim no, we can't. We got to use our quadratic equation. Okay, so using our quadratic formula, we know the number in front of our squared term is 1, number in front of our middle term is 4, and our constant is -1. So for here, we would say x is -b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. So we get -4 plus or minus the square root of 20 over 2, which is -4 plus or minus 2 root 5 over 2. I just simplified my square root and pulled out what I could, which then reduced is -2 plus or minus the square root of 5. All right, that's what x is. But really, we used x in place of sine x. So in other words, we want to solve sine x equals -2 plus the square root of 5, and sine x equals -2 minus the square root of 5. Okay. All right. Well, let's get a decimal approximation here. So if I take the square root of 5, and then plus -2, I'm really solving the sine of x is about 0.236. Okay, how do I solve this? Again, my sine is positive in my first and my second quadrant. So I'm going to hit inverse sine of 0.236. That will give me my first quadrant angle in radians, and will also give me my reference angle for my second quadrant. So if I go through and hit inverse sine of 0.236, I'm going to get 0.238 for my first quadrant angle. And then I'm going to use that as my reference angle. So I'm going to take pi minus 0.238 to get 2.904. All right, over here, well, what is -2 minus the square root of 5? Let's get a decimal approximation for that. I get the sine of x is about -4.236. You can try doing the inverse sine, but notice you can't have a value of sine that's outside of -1 to 1 in the range. So while it may be like, oh my God, no solution there, I think it's really kind of nice when you can just cross it off and say done working. All right, so I hope that helped. You familiarize yourself and kind of get the idea of how you're going to go through and solve each of these. Have fun.